11.2 Series. A series is a special kind of sequence given by summation. Here's a nice motivational example. The first line expresses pi as a sequence of decimal digit, 3.14159, etc. According to this, there's no pattern, no periodicity, no limit. But looking at this a little bit more carefully, you can see that this is actually a summation. 3 plus 1/10 plus 4 over 10 squared plus 1 over 10 to the third power, and so on, just like you have in the second line. And that has a limit. That converges. What do you mean by convergence here this time? Unlike ... previous time, in the first expression, which doesn't really mean anything except it doesn't end, in the second part, the ... part is very, very small after taking the sum of, well, 8th term, or maybe 18th terms, or 80th term, whatever. The ... part will be very, very small and going down to 0. That kind of thing is called series, and it's convergence. We're going to study this in a little bit more detail, with a little bit more precision in our notebook here. And let's begin with a concrete definition. Let's begin with a sequence, AN, and let's define a sequence of partial sums by Sk equals to A1 plus A2 plus all the way up to Ak. And we call this series. According to my definition, a sequence of partial sum and series are the same. Now that we have defined series, or sequence of partial sums, we can consider its convergence. If Sk converges S for some number S, we say the series converges, or it is summable, and we write like this. S is A1 plus A2 plus A3 plus also A. If you aren't already, please make yourselves familiar with this kind of notation. We use Greek letter Greek letter capital sigma to denote the summation. And this denotes summation from n equals to 1 to k. And in general, if you have something like this, the number downstairs represent the starting number. For example, if we start from, say, n equals to 3, then this means we have to begin from 8, 3, kind of like that. And then what if this ends at 6? That means it have to run all the way up to A6. Oops. Needless to say, this ending number has to be greater than or equal to the starting number, otherwise we'll not have any summation at all. If this ending number is not a number but an infinity, then this is an infinite sum. Okay, we define series and then we define this summation notation. What are the examples? There are plenty. The problem is we do not have sufficient tools to deal with any of these in precise terms. We just talked about the meaning of convergence. We don't know when it converges or when it doesn't. Well, we need a little bit more tools, and the first one I'm going to start with is 2.2, nth term test for divergence. There's a reason this thing is called test for divergence. We cannot use it for convergence. In order to conclude a certain series converges, well, it's going to be a heck of a lot more complicated than this. In order to conclude a certain series diverges, sometimes this is sufficient. Sometimes. The statement goes like this. If a certain series converges, then the limit of the general term is 0. So what does that mean? If the limit of the general term is 0, does that mean the series converges? No, in general, no. I cannot emphasize that too much. And here's a nice counterexample right there. Harmonic series. General term is 1 over n. That certainly goes down to 0. But, well, the sum itself is infinity. And, well, here's an estimation. 1 plus 1/2 plus 1/3 plus 1/4 and so on. That goes to infinity. And we'll discuss this in the next segment of the video. I'd like to postpone a little bit more advanced things to the next segment. So here we go. If the series converges, then the limit of the general term is 0. Or equivalently, we take counter positive. Change the conclusion and condition, if part and then change the true-false value. So if, now the conclusion, limit is not 0, like this. If the limit of the general term is not 0, then, now, if the series converges, that was the original, so that goes to then, and the series does not converge. So that's a contrapositive. Switch if and then part, and then change true false values. That's the equivalent. And the proof of the original statement goes like this. It all depends upon this very simple observation. an is Sn minus Sn minus 1. Why is that? Sn is a1 plus a2 all the way up to an added. And the first n minus 1 term is actually the same as, well, Sn minus 1. So if I subtract one from the other, the middle part will simply cancel each other out, and we are going to get only the ending part as this. So we have an equals to Sn minus 1. Upon taking the limit, we're going to get, well, that by the limit rule, we have this limit of Sn minus limit of Sn minus 1, but they converge to the same limit S, so we have to have S minus S equal to 0. Alright, we just talked about the test for divergence, and then we talked about harmonic series diverges. So we also took care of this converse issue for 2.2. Now let's go over to another important tool, geometric series formula. A plus AR squared plus AR cubed, and so on. So what's that limit? Well, here is the conclusion, and the latter part of the conclusion is easier to see. When R is greater than 1 in absolute value, then AR to the nth power will not go down to 0. Absolute value of R is greater than or equal to 1, so AR to the nth power will become either bigger and bigger and bigger, or at least in terms of absolute value, it'll stay the same. Consequently, we do not have convergence toward an going down to 0. So, well, this takes place. Consequently, the original series diverges. So that's the second part. Now, when R is less than 1 in absolute value, then, well, limit of the original this limit of the general term goes to 0. So we have to do something further. We cannot automatically say the series converges, but we can do something about it. And the general formula goes like this: a over 1 minus r. A is the starting term, and over 1 minus r. The proof goes kind of like this. Sn is a partial sum where it's a plus ar squared all the way up to r to the nth power. That's pretty much straightforward. And then here's an ingenious step. Multiply by r, then we get r times Sn. Consequently, we have to multiply r to each term. So a times r is ar. Ar times r is ar squared. And ar squared times r is ar cubed. And so on. And then last term, ar to the nth power times r, we have ar to the n plus first power. Next, we subtract one from the other. What do you get? This ar squared, ar to the nth power, they all cancel out. The middle part all cancel out. And then we have the first and last term. A, the first term, minus ar to the n plus first power. Next, just algebraic manipulation. Factor Sn out, and then divide by 1 over r, and we have this rather important formula here: a times 1 minus r to the n plus first power over 1 minus r. That's actually the geometric series formula for finite sum. But this is calculus. We are not too much interested in finite mathematics. We are interested in limit. So we take the limit, And the limit exists when r is less than 1 in absolute value, so that r to the n plus 1 goes down to 0. Otherwise, the limit does not exist. So what do you have? We have a over 1 minus r. Okay, we have time to discuss telescoping series, but I'd like to postpone that for next segment of the video. I'd rather go over to some example problems here. And let's use the geometric series formula to answer, well, this problem B. And here we go. Summations. Sum will be a over 1 minus r, isn't it? That's the general formula. So let's find out, excuse me, let's find out the first term, a. Plugging in n equals to 1 to this thing, what do you get? E to the first power, so that's going to be, let's explain the font. So the numerator will be e to the first power divided by, now 3 to the n minus first power, so plug in 1, then you get 3 to the 0 power, which is 1, so I don't have to do that. So we got the first term done. 1 minus r. What is r? What is the value that is keep being multiplied? It's e over 3. And then that's the answer. But if you want to simplify, then you can multiply 3 to both numerator and denominator. You can express 3e over 1 minus 3 minus e, if you will. But the final simplification is not really necessary. Oh, by the way, e over 3 is less than 1, so it makes sense. E is 2.71 something, so it makes sense. What if I change this problem into, say, s to the n minus 4th power, for example? The r value will not change. E over 3 will be multiplied over and over again. But the first term will change. If you plug in n equals to 1, then e to the first power is the numerator. Okay. And the denominator will be, plug in n equals to 1, then this will be 3 to the negative third power. So it is positive third power in the numerator. So this will be 27e over 1 minus e over 3, and you can simplify this further if you want to. But let's go back to the original problem. Oh, how about problem A? And you can clearly see this diverges, I think, because square root of 3 over square root of 2 is clearly greater than 1, so the series diverges. And how about problem C? This is 3 times the harmonic series, so it also diverges. Even though the general term 3 over n goes to 0, this series diverges, and it's not difficult to see. And the other problems all require some sort of telescoping series, except for this one, as a matter of fact. Well, as a matter of fact, we can decompose this problem into, well, 2 problems. This one is equal to let's see, this one plus that one. And the first series is a little bit difficult to find out. It'll turn out to be a telescoping series, which I'm going to talk about in the next segment of the video. And this one will be a geometric series. You can find out by this formula, a over 1 minus r. R value is 2/3, that's easy. A value, plug in n equals to 1 and find out. So this is a kind of problem that you'll have to use 2 different types of technique in a single problem. I usually like to do this a lot. In exam problems, I just put plus something, and then you'll have to answer actually several problems in a single queue.